你就可以让他们凹进来也是一个差不多的好像其实不可以去摸懂，就是他的工作。非常贵，只要你这样子不能教学啊。
Right now, what I have is
the tags, the HTML tags,
the table, and output.
So put it between so it doesn't recognize the line correctly. So you want to use the tags to make the table. One tag, just rows instead of if you're streaming, you'll know. If you try to print that out on the table, you'll know that row is table. I'll show you. That would take a while to change it. That's really all we're doing.
Right now, what I'm having to do is I'm having to like the table.
You'll feel able to tell because the table is right.
I try to do this project.
Basically turn out, see how it does this. How you stay for phase
养就好。
I'm just going to shut it down. Taking out pen in the back though? Okay, so pretty sure I'm running too much stuff.
我要养狗，很讨厌猫就是它老爱而且猫不能拉出去。交换的时候，
一起收到。
就是对这种东西狗比较。
So I think try it. You just like, and then TR stands for the row, and then the TH is like the header. If you have to well, it took a while to do all that because you can imagine just modify it. It's pretty tedious. That out and it's nice. So I was like trying to do this. I do like so I was like, how do you do that? So you have these pages and you can put this inside and that's what so you can have this section, 2 tables. Well, basically, you do this whole thing in one day. That's like TD and the TR, so that's what we use and that's why they feel when I showed all the ones that
it's supposed to be like basically.
It has oh, this one was yeah, sorry, it's not 5 seconds. Yeah, it's more than that.
Alright, let's get started. So, just a reminder, today, 5 p.m., your phase 3 is due, and I sent out an announcement on Canvas to clarify the submission procedure for phase 3. You don't have to do anything. Just make sure you upload all your files to the public_HTML folder on Georgia server for your Teams account. And make sure you test your code properly and it's loading and working properly through the Tomcat server instance on Georgia server, right? And other than that, you don't have to do anything. I will give you a little bit buffer time, meaning I will not shut down your access to Georgia server right at 5. Rather, I will give you some buffer time, maybe 20-30 minutes each. After that, I will remove access of all your accounts to Georgia, meaning you won't be able to log in, you won't be able to copy files, and so on and so forth. Okay? Any questions regarding that? And one more thing is, please add a README file to your public_HTML folder. In the README file, please specify at least one user account that TAs can use to log into your website and do testing, meaning you have some user data associated with that user account already, so that it's very easy for them to test your functionalities. Okay, and we work really hard, TAs in particular work really hard, and finish the grading of your phase 2 as we promised, so that give you at least 2-3 days, I think, to review your implementation and fix any bugs, if any, for your phase 3. And if you have a question regarding the grading of your phase 2, you can see in the comment section of your grade, you can tell which TA did the grading of your phase 2 and contact him or her directly and set up an appointment if needed. But I have instructed TA to grade your phase 2 with great leniency, right? So basically, we give partial credit as much as we can. We only deduct points when it's absolutely clear that either the function was not implemented or there's a clear bug in implementation and there was some clearly logic error in your code, right? We'll only take points off for that. Okay. So that being said, any questions? No? Oh, yeah, go ahead.
So if we have a question about our grading for phase 2, we should talk directly to the TA, not to you.
Yes, that's right. So you should only talk to me after you have spoken with the TA and you cannot reach a resolution agreement. For example, TA insists he or she has graded properly, but you feel otherwise. But keep in mind, I did ask TA to grade with great leniency, and but it's still possible that you think you deserve more credit than you got. Then you talk to the TA about it. Okay. All right. Now, before I start today's lecture, I want to give you a quick overview of what to expect, right, in today's lecture and in the final test. So as you know, today will be our last lecture of the semester. Wednesday we will, unfortunately, we miss the Wednesday lecture again. So in fact, we missed a couple lectures this semester due to the collision with various holidays. So because of that, I don't think I will have time to cover the NoSQL discussion. What I will do is I will post some slides on NoSQL that I have prepared on Canvas that you can review after the final test. I released homework 5 last Friday. It will be due this Friday at 5 p.m. You just upload to Canvas. Final test will be Wednesday of next week. Okay? I think it's from 10:30 to 12:30. Is that right? Sounds about right. Right here in this lecture hall. And the final test, the style of the final test will be the same as what we did in midterm, meaning is subject to the same open book policy, right? I don't want to repeat myself, but basically you can bring your laptop, you can access anything from the Canvas class homepage, all the materials I have posted over there, but that's the only website you have access to, and only those materials, right? You're not allowed to bring any other personal notes or any other related website that you cannot access, right? You can only access that particular website. And the scope of the final test will be homework 4 and homework 5, plus quiz 4 and quiz 5, which is to be released once homework 5 is due, after I release the homework 5 solution, okay, on Friday. Okay, we are still going to cover, I'm going to use maybe up to maybe 15 minutes of today's lecture time to cover the remaining part, what we need to cover. We're almost there. Then I will take 10-20 minutes to briefly talk about NoSQL, just give you an overview of what it looks like. And then if we still have time, I will open the floor for some additional questions if you have any. That being said, I will if you have any questions regarding the scope of the final test, you can ask me now.
So it won't cover anything from the first half of the class?
That's right. No. So basically, start from the discussion of functional dependency. Okay, goes to transaction, then goes to disk management, buffer management, and files, as we will be discussing today. Yes. Can you speak a little bit louder?
So the test won't be on the first step that the first midterm was on?
No, just in my reply to his question, right? The test will start after the midterm test, the content covered by the test. Does that make sense? Okay. Any more questions? Or we're good to go? All right, so today, let me continue on where we were. Yep.
So is that the same strategy, study for the test, is study homework and apply?
Yes, let me get my vector working before I answer the question. Yeah, so the question was, should we adopt the same strategy for preparing the final as we did for the midterm? Yes, totally. So the problem in the test will be exactly the same style of question you have seen from your homeworks and your quiz. I won't test any new type of problems. That being said, the best way to prepare for your test is to make sure you understand those problems from your homework 4, homework 5, and quiz 4 and quiz 5. You may not be able to solve those problems by yourself when you first attempted to do it, but at least you should try to make sure you understand the solution I have posted. And make sure you can solve those problems independently by yourself without discussing with your friends. The time allocated for the final will be, roughly the amount of problems and the time allocated to the final will be a little bit longer, right? 2 hours. But the amount of problem will be similar to the amount of problem you have seen from midterm. Meaning, if you know the material well enough, you should be able to solve the problem, and with 20 minutes each left to do a check and so on and so forth, right? But if you end up spending, for every problem, you need to flip through the slides and find out the concept, trying to understand what's going on, obviously you will run out of time. You won't have enough time, right? But if you know the concept pretty well and you just use the slides and the open book policy as a quick reference, then you should have enough time. You cannot rely on open book policy as a way that you're gonna understand, pick up the solutions or the concept on the fly, then solve the problem, and still expect to have enough time. That obviously won't be the case. Okay?
In homework 5, problem 4, it says, in the description it says the table below describes the contents of the bucket pool, but there is no table below.
Let me see. Is it in the next page, I believe?
It's above, actually.
It is above? Right, is that for the problem?
Yeah, because LaTeX might have rearranged the figures a
So
little
is the
bit.
table above?
Yeah, that's right. Okay. All right.
Okay.
Yeah, go ahead.
So it's the same open book policy on the final as.
Yes, that's right.
Okay.
Yep. Basically, you can bring your laptop, either access the campus website during the test, or you can pre-download those lecture slides, homework solutions to local disk so that you don't have to access internet. And you are not allowed to bring any additional notes that you prepared. Okay? Question on this? No? Good. Okay. So, a quick overview of what we have discussed. We talk about storage hierarchies. We talk about hard drive in particular. Then we talk about for management. Before I proceed, I don't know why it's not showing right there. Is it showing up? Okay, cool. So before I proceed, I just want to spend maybe 1 or 2 minutes to briefly talk about one thing that I didn't cover in my slides, which is in today's computer, in addition to memory and hard drive, you often also have access to a solid-state drive, SSD, often known as flash disk. So what's the difference between flash disk and hard drive and memory? Okay, here's a catch, right? Your main memory is volatile, but it's really fast to access. It operates under this RAM model, random access model, meaning any memory space you try to access is give you a roughly uniform cost and really fast. But memory is expensive, meaning dollar per byte is the highest among all the storage media you can think of. Hard drive, on the other hand, dollar per byte is much lower compared to memory, but it's slow to access, okay, for the reasons we have explained. But the good news is hard drive is non-volatile, so it's good to serve as a storage media that provide persistent data storage for your database. If you think about SSD, SSD is somewhat in between. Solid state drive is also non-volatile, meaning if you push data to it and you remove power or your system has crashed, data stored on SSD is persistent. Okay, so from that point of view, solid state drive is more similar to hard drive than it is to your main memory. Okay, dollar per byte, solid state drive is in between hard drive and main memory. Okay, it's not as cheap as hard drive, but it's not as expensive as your main memory. However, a benefit, a really attractive feature that solid state drive has is its random access speed is almost as good as sequential access speed. This is not the case for hard drive, right? For hard drive, we have explained sequential access is much faster than random access. What's the reason for that? For random access, you have to pay a 6-time delay and rotation delay for every page you're going to read. But if you do sequential access, you pay one 6-time delay, you pay one rotation delay, then you continue, you read the sequential blocks from this in a continuous fashion. In some sense, the 6-time delay and rotation delay you paid are amortized over multiple pages you're going to access from the disk. That make sense? So it's amortized or averaged over hundreds of blocks you're going to sequentially read from hard drive. So sequential access is much faster than random access. For this reason, hard drive is not compatible with this random access model we talk about. Obviously, the cost of accessing a particular block depends on the relative location of the block to the current position of the head of your arm. So it's not valid under the RAM model. But SSD, solid state drive, for solid state drive, random access is almost as cheap as sequential access. That's the key reason why solid state drive is much faster than hard drive. That's probably the reason why people are willing to pay a higher price to get that solid state drive. You probably have that experience. If your computer, you install your operating system on solid state drive versus installing your operating system on hard drive, the former approach is much faster. For that reason, random access is much faster than random access from hard drive. But fundamentally, what's the reason for that? The reason for that is the physics governing the manufacture of solid state drive is very different from the physics governing the manufacture of your hard drive. In solid state drive, you no longer have this mechanical arm moving around and rotation, all that stuff. Solid state drive, the physics behind solid state drive is similar to the physics in main memory, meaning is the storage media in a solid state drive is made of electrons instead of magnetic field. So they travel almost at the speed of light. That's why random access is really fast, almost as fast as sequential access. But you may wonder, if that's the case, why solid state drive is non-volatile, but main memory is volatile, right? There must be a trade-off, right? The trade-off is, in solid state drive, you cannot do in-place update. In order to make solid state drive non-volatile, you cannot do in-place update. In-place update meaning you write over the bytes that was originally stored on a block. You write it over directly. In solid state drive, the way it works is as follows. I will explain on the whiteboard. So in solid state drive, you have something called, you have similar concept like block, right? Just like blocks in hard drive. Of course, a block in solid state drive typically is much larger in size, maybe 128 kilobytes or things like that. Now, what happens in solid state drive is, so these are blocks, right? Block 1, block 2. Initially, they do not store any data, right? Once you start pushing data into it, and let's say you want to do an update, so you have some new content you want to write back to this part, you cannot do in-place update. You cannot simply run over this block. What you have to do is, you have to copy this block to a special region. Okay, special region. That's called eraser blocks. Eraser blocks. So you copy it over. Does that make sense? Then you write this whole block, the new content of the block, to this eraser block. Then you write it back. Then you erase this block, and you write it back. This operation, you have to do this eraser block operation for any update you do, no matter how small the update is. Even if you try to update a single byte on a block on your SSD drive, you will need to write to this new block and erase the entire block of the original content, then write it back. Okay, does that make sense? And this process is very expensive, as you can tell. Very expensive in terms of the time it takes, and in terms of the lifetime, in terms of the impact to the lifetime of your solid state drive. And that's why, if you have experience with your solid state drive, you will notice that if you do a lot of write, you update your solid state drive all the time, then the expected lifetime of your solid state drive will be dramatically reduced. For this reason, okay, each block in a solid state drive can only go through this eraser block operation for a predefined number of times. Because over time, the physics behind it will lead to the inability to store data anymore. But at that point, your solid state drive becomes useless. So not only writes are expensive in terms of time it takes on a solid state drive, but more importantly, it reduces the lifetime of your solid state drive if you do writes all the time. Okay? So for that reason, if you think about the relative relationship between memory, solid state drive, and hard drive, it's really a trade-off and compromisation among different dimensions, right? Among the price you are willing to pay, how many updates you are going to do, and whether you want to go with non-volatile or volatile storage media. Finally, whether you want to reduce the cost of doing random access over a large amount of data. If you want to reduce the cost of doing random access over a large amount of data, you want to have this intermediate layer that's made of solid state drive in between memory and your hard drive. Of course, this is a hardware solution, right? So what I mentioned is a hardware solution. There's also software solution that you can use to reduce the cost of random access, which essentially is what I'm going to discuss next. Okay? So far so good? Okay, so that being said, we're going to move on to the next discussion. So we talk about storage hierarchy, we talk about buffer management, we talk about disk space management. And in particular, now we understand how we retrieve a particular block from hard drive, and we need to buffer that in the buffer, cache that in the buffer, to serve the higher layer requests. But how does the database management system organize a table, right? A table has a large number of records. How does DBMS organize those records? So conceptually, what happens is you have what we call files of records. Essentially, every single table in your database management system is essentially a file on disk. And a file is a collection of pages. Here, each page is a single disk block. It's a single disk block. And each page contains a collection of records. And conceptually, the file must support the following operations: insert, delete, update these records, fetch a particular record, search for a record, and scan all records, or scan a range of records, right? For example, return all student records with age between 20 and 22. That's a range, scanning a range of records. So you need to support those operations. So how does DBMS organize those records in a file so that it can efficiently support these operations? That's essentially what we're going to discuss next. So we're going to focus on this particular thing called heap files. A heap file is basically a very rudimentary organization used by DBMS to organize a collection of pages. In particular, a heap file is unsorted, meaning those pages are just randomly grouped together without any particular semantics or particular order. Okay, that's essentially the high-level idea of a heap file. And a heap file needs to support this following record-level operations, such as keep track of pages in the file, keep track of free space on each page, and keep track of records on a page. And there are many different alternatives. We will consider two particular designs that are popular in many different data management systems. The first approach is to implement a heap file as a linked list. In this picture here, each rectangular box represents a page or a disk block. And within that page, you basically have a set of records. I will zoom in to that page later on. For now, let's use this page as a black box that has a set of records. Okay? I'm going to have, in this first approach, I will have two double linked lists of pages. The one on top, the linked list on top, colored by blue colors, those rectangles, those represent what we call full data pages, meaning there's no space left in those pages to hold any additional new record. Whereas down below, the list down below is the other pages, meaning those other pages with some records but still have space left for you to push more records into those pages. And then you have a header page that links these two lists together and stores some metadata information about the file, such as which table it corresponds to, how many pages I have in each of the lists, and so on and so forth. Okay? So this particular structure, if you think about it, it supports the insertion of record very easily. Whenever you try to insert record, I will simply go down to the second list and find a page with space and insert record over there. It also supports the scanning of records. I simply scan through this linked list on both lists to find the record I want to search for. If you can do search, you can also do update. Right? You find the record, you pin the page to the buffer, make some changes, the page will become dirty. When the page is to be replaced by the buffer manager, it will be written back to disk. Does that make sense? So far so good? So that's the first organization. The downside of this organization is what? The downside is also very obvious, actually, from this picture, which is if you want to do a random access to a particular page, it is kind of expensive, right? Because you always have to start from the header page and go through the linked list to find the page that you want. Does that make sense? Which can be expensive if your list is long. So for that reason, people come up with a second approach. In this approach, I no longer distinguish full data pages and data pages with free space. I will mix them up together. I just call them a collection of pages. But then, in order to remember whether a page has space or not, I will produce this little rectangular box. each page that stores some metadata information about that particular page, such as number of records in that page, available space, and so on and so forth, and page ID. Then these are what I call the directory entries. Directory entries. So I will have one directory entry per data page I have. Now I will group these directory entries into pages. Okay? But here is a key observation, which is the size of each directory entry will be much smaller than the data page it represents. Each data page is 4 kilobytes or 8 kilobytes. That can, if, for example, if your record size is 100 bytes, for 4 kilobytes page, you can store roughly 40 records per page. For 8 kilobytes page, you can store about 80 records per page, right? If your record size is 100 bytes. But the metadata information, this directory entry about the page, is really small, probably just a couple tens of bytes, right? You basically store the page ID. By the way, these pointers are conceptual pointers, right? Essentially, these are page IDs, block ID, okay? You store the block ID, you store the free space available on that page, and maybe just number of records on that page, that's it. So each directory entry probably just occupy less than 100 bytes. So you can group a lot of these directory entries into a single page so that the number of header pages you have, is much less than the number of actual data pages you have. Does that make sense? And the benefit of doing this way is that now you can do random access. In order to find a particular page, what you do is you scan through the header pages, which is much less in number of blocks compared to the actual number of blocks you have. So you can quickly scan through these guys, and whenever you find the direction entry correspond to the page you're looking for, you can look up that page directly. Of course, the trade-off is now the overhead. The storage overhead is higher, right? In this case, I only have one header page. In this approach, I will have multiple header pages. So there is a trade-off over there. Does it make sense? Very intuitive approach, right? So these are heap files. Now, I'm going to talk about indexes. Yes, go ahead. The gray small rectangular box, yes.
Each of those is a header page?
Each of this is a directory entry, a collection of them is a header page. How many directory entries you can pack into a header page, that depends on your page size and the size of each directory entry. You can do a quick calculation to figure that out. Does that make sense? Fantastic. Now, indexes, a lot of you talk about indexes, right? Indexes, I give you a sneak preview here, then we will have a little bit more discussion on this later on. Indexes is nothing else, an index is nothing else but a particular organization that you have introduced to facilitate the retrieval of these pages. For example, binary tree is an index because it facilitates a faster retrieval of the item you are trying to search for. If you replace those items at the leaf level in a binary tree with these pages, then your binary tree becomes an index over those pages. Does that make sense? That means that there are many different ways of introducing different indexes, and they serve different purposes. And we will have more discussion on this later on. Okay, so that's just a quick overview of index. Later on, we'll come back to this point. Now, this is file level organization, right? How they organize pages together. Next, we're going to look into each page. Right? Now we're going to zoom into a page, which, keep in mind, has a collection of records. We're going to basically talk about two things. One is, how do you organize those records? And how do you organize a single record? Right? Once we understand those two things, we understand how a page is organized. For this, I'm going to talk about how to organize a record first. So there are two cases. One is fixed length, one is variable length. We had this discussion very early on in the semester when we were talking about different data types in a database system, right? variable character array and fixed length character array. And I said then there is an impact to your storage engine for variable length character array, varchar versus char character array. Right? Now here is a more in-depth examination of that problem. First of all, let's assume we're dealing with fixed length record. Fixed length means that the data types that you have used in the schema of your table are all fixed length, such as integer, float, character array. You are not using varchar, variable character array, which will make your record variable length. Okay? If you're dealing with fixed length data types, things are much easier, right? In particular, the number one thing you need to do when designing how to store your record back to a page is to make sure you can do parsing of your record properly. You can pass a record into different fields it has with regard to the schema you have specified for that. For example, I have a student schema that has student ID, student name, login, and age. Let's say I have 4 values. Suppose I'm using fixed length for the student name and the other ones are integers. So it's all fixed length. The most important thing you need to support is to be able to, if I give you a student record, you need to tell me what's the value of the student ID, what's the value of the student name, what's the value of the age, what's the value of login. Does that make sense? In order to do that, you basically need to do parsing of this sequence of bytes I give you. I tell you this sequence of bytes represent a single student record. You need to somehow pass that sequence of bytes into different fields that student record has. Does that make sense? For fixed length record, this is super easy. Why? Because for fixed length, you know exactly the offset location, meaning these lines, these boundary lines, between different fields in a record. Where you find that information from? You find that information from the schema of the student table. Because in the schema you specify the data type, and once you know the data type, if it's fixed length, you know how many bytes that particular type will occupy. Then once you know the base address of a record, you can use the length information of each data type to easily figure out the offset of different attributes. Does that make sense? So far so good? For variable length records, things become a little bit trickier. For variable length, this becomes trickier. There are basically 2 ways to do this. One is you add a special delimiter, like a $sign. Of course, $sign cannot be used as a delimiter because $sign can appear as part of your value, right? Then you confuse yourself whether it's a delimiter or it's part of your value. So you use some character that's reserved as this special delimiter that doesn't appear anywhere in your database. Suppose $sign is one such special delimiter, then you can do parsing without problem, right? You just keep going until you meet a delimiter, you know that's the starting of a new field in your record, okay? The downside of this approach is that it doesn't support random access into different fields in your record. For small length record, this is not a problem. You basically do a linear scan to parse out the particular attribute field you want, but for really long record, this can be expensive, right? Because you may need only just one attribute value. Suppose you're doing a projection. In order to do that projection of that value, one value, you need to scan through the whole record. If the record is long, this can be expensive. For that reason, people also introduce the second approach, which is similar to this idea, but you apply this in a record level. You have this, what we call the directory entries attached to a record that basically these are the offset of these boundaries between different fields. That way you can do random access into any record field very quickly. They are drawn as, in this picture, they're represented as pointers, but in reality they're just offset values. 10, 30, 45, that tell you the number of bytes indicate the starting address of a particular attribute field. Okay? What's the downside? Okay, that's a benefit of second approach, right? What's the downside of second approach? Well, the storage overhead is higher, right? In the first approach, the storage overhead is what? Is 1 byte per field. Because a delimiter is a single character, that's 1 byte. A character is just 1 byte. So if you have 4 fields, you only need what? 3 delimiters, you only need 4 bytes, right? Or 4 bytes, if you want to remember the end of the record as well. However, in the second approach, these pointers are offset values, which is an integer. You need at least maybe 2 bytes, or maybe even 3 or 4 bytes, depending on how large your record length is. The largest offset value you need to encode. That's definitely more than just 1 byte. Well, 1 byte can only encode up to the value of 8 in decimal. Does that make sense? So the overhead is slightly higher. That being said, so that's how we organize attributes in a record. Lastly, in order to understand how we organize records on a page, now we understand how each record is organized. We need to understand how we organize a bunch of records in a page. There are again 2 cases. One is fixed length record, the second is variable length record. Variable length record is much more complex. I will ignore that discussion in this particular course, but I have a slide for that. So I will focus on discussing fixed length record organization. Fixed length record organization is actually fairly straightforward. Again, there are 2 approaches. On the left-hand side, this whole thing is a page. This is a page, and each thin, long, rectangular box is a record. So this is a record. Okay? Suppose this page can hold up to n records. How do I calculate that value of n? Well, I use the page size, the size of the page, and the size of each record to figure out how many records I can pack, in the best case, into a page. Does that make sense? For fixed length, this is very easy to calculate because each page is fixed length. Now, what I will do is, in this first organization, the white space represent records, and the black region represent free space, meaning those space that are on this page that are still available to store additional records. So one distinct feature of this organization is the record space, the white space, is consecutive. It's a continuous collection of what we call slots from this page. A slot is a continuous sequence of bytes that's large enough to fit just one record. That's what we call a slot. With this organization and the fact that you're dealing with fixed length record, all you need to do is to remember the boundary between your record space and the free space. You do not need to remember these boundary lines per se because they are fixed length records. Does that make sense? If I tell you the base address, and let's say the 10th record I'm trying to access from this page, I can easily calculate the offset, the starting address of the record, using the base address plus 9 times the record length. That must be the starting address of the 10th record. So all I need to know is the boundary between record space and free space. I need to remember that. That's essentially translates to how many slots are occupied by records, which is n in this case. So I have n records on this page, which have occupied the first n slot. So I only need a single number at the end of the page, which is n, to remember how many records I have, or how many slots I have occupied. So pretty good? So it's very easy. The downside of this approach is that insertion is easy, right? Insertion, I just figure out the value of n, I will insert to the n plus 1 slot, and then I update the value of n to n plus 1. Deletion becomes expensive though, because if you delete a record, what you have to do, you have to compact the record space, because you need to make sure the record space are contiguous. So you need to move all the slots coming after the record to be deleted, move them ahead by 1 slot space, and update this value n to n minus 1. So deletion can be expensive. Updates is easy, right? Updates, you simply write over that particular slot representing your record. It's fixed length, so you never need to worry about the new record, the new updated image is longer than the slot allocated to that record because you don't have to worry about that issue because it's always fixed length. That make sense? To address the challenge faced by deletion is expensive, right? In this first organization. There's a second alternative approach, which is, again, similar to this idea, right? Instead of pushing all records into a contiguous record space, I will allow records to scatter around on a particular page. So they can be stored anywhere on this page. But then I need to remember where they are, right? Because I can no longer simply do an offset calculation to figure out, oh, you need the 10th record, it must be the 10th slot. It may not be, 10th slot might be an empty slot. However, I do not need to use pointers for these purposes. Of course you can, meaning store explicitly the offset values of each record, but that will be expensive. Right? Offset value can be a big integer number, require 2, 3, or even 4 bytes to represent. That make sense? Knowing that I'm dealing with fixed length, I can reduce this overhead by storing what we call a bitmap. A bitmap of size M, capital M. What's M? M is the total number of slots I have, where each slot equal to the size of one record. Then I simply use 1 or 0 on this bitmap on the corresponding position to indicate whether the corresponding slot is holding a record or a sequence of jump bytes. That allows me to quickly figure out where a record locates at with a single bit overhead. In total, my overhead is M divided by 8 bytes because you're using M bits. So how do you figure out the value of M? If you know the page size and you know the record size, you should calculate the value of M as follows, right? You need to reserve this many bytes for the bitmap, then you divide by your record size. And you take the floor of that. That should equal to the value of M. P is page size, R is record size, M is this value M. That's the calculation you need to do to figure out the value of M. Does that make sense? Yes or no? Look at this formula. You have P bytes in total to use. You need to reserve M divided by 8 bytes for the bitmap. Those remaining bytes are available to store records. Each record takes R bytes. Divided by R, that's the maximum number of records you can hold. Take the floor of that. That must equal to M. That's essentially the number of records you can hold on this page. Okay? With that, I stop right here. And then there are also a variable length record, which we will skip, right? If you're interested, you can review this yourself. But variable length record is much more involved. The organization of them is much more involved. We will choose not to discuss them in this lecture, in this class. Okay? Now let's discuss the next topic. Access message. Now we understand how we organize blocks, how we organize attributes in a record, and how we organize records in a page. We're ready to discuss just a little bit how a database kernel functions. Meaning, how do you retrieve those blocks back from disk to support you SQL execution, SQL execution. So this is the general model, the abstract model we're going to use, right? This is the processor, and this is memory. If you just have these two layers, you're going to use this random access model we talked about last time, right? RAM model. However, now the picture changed a little bit. You have processors, you have memory, and you have disk blocks. And there's a boundary line between memory and the disk, meaning that because your memory size is limited, buffer size is limited, you may occasionally need to visit disk and bring pages from disk back to memory, and you may occasionally write pages from memory back to disk if those have been updated since it was read into buffer last time. And this is what we call block I/O, input and output operations. The whole point is to try to minimize this cost because block I/Os are expensive. So one solution is to buy a lot of memory, right? So that you never need to worry about block I/O, but we all know that's not a scalable solution, as I discussed before. So we're gonna talk just a little bit how people have designed different software solutions to minimize these I/Os. And that's essentially the idea behind indexing. So to facilitate our discussion, I'm going to use these parameters. N is the number of items in the problem instance. In our case, N is the number of records on a particular page. For example, you have 1 million student records, N will be 1 million. B is number of items you can hold per block. For example, if your page size is 4 kilobytes, and each record is 100 bytes, then number of records you can hold per block is what? It's 40. So B will be 40 in that case. Does that make sense? So you calculate the value of B using P divided by R roughly. Of course, this is an approximation because you need to reserve some space on a page to store some metadata information such as page ID and so on and so forth. But roughly, B equal to P divided by R. P is page size in bytes, R is record size in bytes. And you take the floor of that. Because whatever remains is not enough for a whole record. Does that make sense? So that's the value of B. Number of M is number of items that fit in memory. Note that M is number of items fit in memory, not the number of bytes, not the number of blocks, but number of items, number of records you can hold in memory. So that given M, you can calculate number of pages in this memory buffer, which is essentially M over what? Someone tell me? If I tell you M is the total number of records you can hold in your memory, how many blocks this memory has? How many blocks this memory has? Given the setup, it's going to be M over B, the floor of that. Why? Because B is number of items in a single block, in a single page. M is the total number of items you can hold in memory. So M over B is the total number of blocks you have in your memory. Does that make sense? Question on this? No? Good. What about number of blocks for this table? N is total number of records you have, right? B is number of records per block. Then how many blocks you have on this file? How many pages you have on this file? It's just N over B, right? But this time you need to take the ceiling of it, not the floor of it. Why? Because for whatever remains for the last few records, even though they don't occupy a whole block, you still need to allocate a block for it. For example, each page can hold 5 records. I have 12 records. How many pages I need to store this file? 5 records for the first page, 5 records for the second page, and 2 more records in the last page. In this case, B equal to 5 and equal to 12. Does that make sense? Okay. And let's use T to represent the size of your query output, number of records in your output. Okay. So those are the discussion we have, and we have one assumption that M is greater than B squared. This assumption is important for some really interesting algorithm in the analysis of those algorithms, but for the purpose of this class, this actually is not that important because we just don't have time to cover those more interesting, more complex algorithms. I will focus on some really simple cases, right? In which this M greater than B squared condition is not important. Let's start with some basic comparison in the RAM model. So in the internal memory model, is what we call the RAM model, which is when you assume all your data are fit in main memory. That's essentially, you guys probably never realize this, but that's essentially the programming model you've been using in all the code you have written so far. But in reality, if you go work for Microsoft or Google or Facebook, you will have big troubles if you make the assumption. Right? In particular, let's look at some comparisons. Instead of looking at this value, I'm going to show you some really simple examples. Right? In internal memory, first, so let's look at the first one. First one is easy to understand. If I have n item, n is total number of items I have. In internal memory, if I want to do a scanning of all your items, suppose you have an array, I want to do a linear scan. What's the cost of that? We all know the cost of that is n. You simply look at each one item once. That make sense? For external memory, what's the cost of this? For external memory, it's no longer n. Of course, you can still read item one by one, but that will be super expensive if you write your code like that. Because if you read item one by one, when these items are stored on disk, for n item, how many IOs you are paying? You are paying n IOs. But if you do pre-fetching, meaning you fetch block by block instead of item by item, how many blocks you're paying in order to scan all items? It's simply n over b instead of n. There's a huge difference. Because the value of b typically is at least 40, 50, or maybe hundreds. Does that make sense? Right? B is number of items you can hold in your block. Suppose each record, let's use some real values, right? Let's say your page size is 4 kilobytes, record size is 100 bytes, or 40 bytes. Let's say to make the math simpler to understand, what's the value of B? B is 100. N IOs versus N over B, in this case, N over 100, there's a reduction of 2 orders of magnitude difference. And that's why if you look at Java, you look at C++, they always encourage you to do buffered read or buffered write from disk, rather than reading item one by one from your code. For this reason. There are other costs for sorting and promoting and sorting. I will come back to these values later on, but for now let's just look at the scanning. Let's look at some basic data structures and see the difference in the way you should write your code to represent those data structures. You all know what's a queue, right? How many of you know what's a queue? Right? First in, first out. FIFO queue, right? In internal memory, this is easy. I push, I pop. So pop is like this. I pop one item at a time. That make sense? So the cost of that in internal memory by the way, this n versus n over b is demonstrated using these two guys. This is, imagine this is a block, this is one item. This is a block, this is a single item. If you read item one by one, what happens? If you read item by block, what happens? Seriously, that's exactly what happens. Does that make sense? Yeah. For internal memory, it doesn't matter whether you're reading one item at a time or you're reading multiple items at a time, because it's random access model. In internal memory, the cost for you to read this many items, let's say each block has 3 items, the cost of doing this is exactly 3 times of this. So whether you do it one by one or you do all 3 at a time, no difference, random access memory. But on disk, huge difference. You read one item, remember, you always access item, no matter how small or how big it is, from disk in the unit of block. If you read just one item at a time, you're reading a block anyway, you're doing a random I/O for it. But if you read a lot of items at a time, you pay one random I/O that's amortized over multiple items. So the cost is much smaller. That's the point. Okay? Now, for internal memory, for queue operations, for queue operation, pop or push is order 1. For external memory meaning involving a disk. If the naive approach is also 1 I/O for operation, right? In order to do this pop, what you need to imagine this is a block, right? This flat box is a block. In order to pop one item, you need to read that block, remove the item, write it back. Right? Pop again, you need to read that block again, write it back. So it's 1 I/O per operation. Does that make sense? Can you do better? Can you do better? Yes.
Read the whole block, do all the pops, and then write it back.
Read the whole block. Let me modify what you have proposed a little bit. Read the whole block when you pop, and pin the page in the buffer. Do not unpin it. Make sure the buffer manager not to replace this page until you have popped all the items from that page. Then write it back. What's the benefit of doing that? You're paying 1 I/O per B items. How many items you have in a block? B items. So you're paying only 1 I/O per B items. So the amortized cost now become, instead of this, become 1 over B. So that's the idea. So you pin the page in the buffer, you keep popping items from it until you're done. Now you unpin the page. Mark it dirty, write it back. Does that make sense? Yes or no? Only at the boundary, now this is 1 I/O. You read the next block. What about push? Same thing. You create a new page, but you pin this page in the buffer. You keep pushing until when you're done, you unpin the page and mark it dirty, so buffer manager will write it back. So the I/O cost is 1 over B instead of 1 I/O per item per push. So far so good? It's a very simple idea, but it gives you, if the value is B is 100, it gives you 100 times performance improvement if you do this. Do you follow what I said? Yes? Okay. For stack, it's the same thing. You do the same trick. Now, I will ignore the cost for sorting, promoting, and sorting. I will talk about only sorting. I will not talk about sorting and promoting in this class. How these numbers come about. If you're interested, you can talk to me offline or take the grad level data class, which will have detailed discussion on it. Sorting and promoting in external memory is actually not that trivial. Sorting in main memory, you all know, use quick sort or whatever. But what if I ask you, imagine Google has a machine with only 256 gigabytes of RAM. That's the typical size of RAM you have on a super powerful server machine. But you have 2 terabytes of data to sort. You only have 256 gigabytes of RAM. How do you do this sorting? It's no longer that trivial, right? How do you do sorting in that case? Okay, now we're gonna focus on heap file and sorted files. And before I do this discussion, I want to show you a simple experiment. I haven't done this experiment for a while, so I hope this works. If it doesn't work, bear with me. I'm going to need to enable network. It works, okay. Server is normal. So remember, say there's 2 Excuse me, can you turn off the lights? There are these two tables. Yeah, I think this is here. Yeah, thanks. Test 1, test 2. Okay? I'm gonna show create table test 1. And before I do that, I will describe test 1, which is essentially a simple table with ID, name, and rating, right? Person with rating. And if you look at the create table statement, the primary key is ID, key is rating. There's a B plus tree on the rating table, on the rating attribute. I will talk about B plus tree briefly later on, but it's just an index. A special way of organizing those blocks on this page so that it's faster to retrieve records based on the rating value. If you look at test 2, and I show create table test 2, it's identical, but without that B plus tree on the rating attribute. Yes or no? So what I will do is I will do a simple select and into, if you look at MySQL, so I will do this. I will simply do something like this. Okay? And in order to avoid the cost of displaying the output, I will write the output to a temporary file instead of displaying all the records in the terminal, right? Because that will take a long time. So before I do that, I will first do a count from test 2 and test 1. So they're the same size. They have both of them have 5 million records. And the rating value, I can tell you, is from 1 to 100. Rating value is from 1 to 100. So what I will do is I will do select ratings from test 2 into so this will select roughly 5% of the records, right? Because, by the way, I used uniform distribution when I generated those 5 million records, uniform distribution on the ratings. So those will select roughly 5%, which is about 250K records. That make sense? Yes or no? Do you follow? Where? Select ratings from test 2 into alpha. Ratings to 90 and you have adding signature for 90 that corresponds to this. It's weird.
Do you have to waive the file extension?
Huh?
The file extension? That's fine.
Can you remove this? Okay. So something wrong with this. Maybe. Okay, so this is, let's see how to do this. Let me see whether I can figure this out very quickly. Let me see how I do this. So maybe I change this to this, okay? Instead of, I just do a count. But this will do the same thing, okay? Let's see how long this query will run, okay? Now I will do the same thing using test 1. Remember, test 1 has a B+3 index on the rating attribute. So this experiment is not doing so well. Let me try again with this. Okay, so there's a cache effect over there. Now see the difference, okay? I will run these two experiments one more time. Test 1 is the table with the index. And test 2 is the table without the index, okay? Same table, exactly same set of data. Okay? Do you see the difference? And this is just counting, right? There's some security privilege issue with my account that I cannot write to output file. But imagine if you write all this output to the output file, the second approach will take even longer time. The gap will be even more significant. Okay? But even in this case, there is, let's say, more than 10-fold of difference, right? The first query is 10 times more faster than the second query with the same data, same table, same distribution. That make sense? Why is that? Why is that? Yes? Yes, it is because of the index. But fundamentally, how an index works, that's essentially what we're going to discuss in the next few minutes. Yeah, go ahead. Buffer play a role as well, but the major difference of the two, both queries are available to use the same buffer, by the way, right? So it's fair, the buffer play a fair role to both cases, right? Why there's still a huge difference here?
I'm assuming the one with the B tree was maybe stored in some way that it's like a binary tree, and so that finding that data, there's like only log n.
That's exactly what's going on. That's exactly what's going on. I want to now extend that discussion, elaborate what he said in more details in the next few slides. It's actually not that hard to understand. Okay. So allow me to move back to the slide here. The test 2 table that you have just seen is using simply a heap file. There's no sorting, no organization, no index whatsoever. So it's just a heap file, collection of pages in no particular order. The test 1 table is using a B+3 indexing structure. So the difference is, here is the cost model for our analysis. I already explained to you. Excuse me, do you mind? Switch on lights again for me? Thank you. N, remember, is the total number of records you have. B is number of records per block. So the total number of pages you have on a file is N over B, if we ignore the flooring or ceiling effect of it. D is the average time to read or write of this block. Actually, we can ignore this value of D for the most part because this is a uniform cost. No matter whether you're using index or you're simply reading a block from this, it's just D seconds per block, D milliseconds per block. So that's a simple setup. We're assuming single record insertion and deletion. We're assuming when we do selection, we're doing equality selections. For heap file, we assume the insertion always append to the end of files, to the last page. For sorted files, there are two alternatives. One is sorted file, by the way. Sorted file is just a heap file, but all records are sorted in a particular order. For example, I sort all student records based on the rating value you have, from the smallest rating to the largest rating. Otherwise, it's exactly identical to a heap file, but the only difference is records are sorted. And there are two alternatives here. One is there's no space left between any two records, so that the whole file is 100% utilized. There's no free space left in any page. It's always compacted, which is essentially the second operation, meaning after you delete a record, you need to compact all the records so that you don't leave a hole in between. The other operation is I don't care. I leave holes in between. I will somehow recycle them later on. There are these two alternatives. Just keep that in mind. Let's look at a side-by-side comparison of the two, heap file versus sorted files. What's the cost of scanning all records? What's the cost of scanning all records? N or N over B? N over B. Remember, we're doing this in terms of I/O, number of blocks you're doing. So N over B. This is the same for both cases. If you want to count the time, it's N over B times D. By the way, this D value here, for both cases, it should not be random I/O time. They should be sequential I/O time because you're doing a sequential rate over N over B blocks. In other words, you pay only one sync time delay and one rotation delay for this N over B blocks. The rest of time is just wait for this to rotate N over B blocks to go under the head of your arm. So basically, it's dominated by how quick your disk can rotate N over B blocks. Does that make sense? Yes or no? What about equality search? How do you do equality search? By the way, a sorted file is kind of like conceptually you have a binary tree on top of these blocks on disk. Because the records are sorted by the value, for example, the reading value. And we are making the assumption that we are doing an equality search on the attribute or attributes. It can be multiple attributes, right? Used for your sorting. In that case, you sort by the value of the first attribute, you break the type by the value of the second attribute. We're assuming that we're doing an equality search on the sorted attributes. Otherwise, a sorted file is just like a heap file. If your students are sorted by reading, but you're doing a search on age, the fact that it's sorted by reading doesn't help you in any way. Does that make sense? For equality search, to do an equality search over a heap file, what's the cost? Can someone tell me? How do you find a record with a particular value, essentially? How do you find, for example, reading equal to 5, for example, going back to this. How do you do this query? Of course, I'm not going to execute this because if I do execute this, somehow it doesn't allow me to write to a file. It will export too many records to the screen. Right? Because I have 5 million records, even this is 1%, that's a lot. 50,000 records. But how do you do this in test 2 if it's not sorted? Can someone tell me?
You have to iterate through.
You basically have to scan through all records. Right? Because you don't know where that record locates at. So it's N over B. N over B in the worst case, however, if you know, here's the important assumption, if you know you have only one matching record. Suppose you're doing equality search on a key attribute. You know, I tell you there's only one matching record. Then there's the optimization you can do, which is as soon as you encounter that record, the page holding that record, you can stop. Because you know there's only one record. So the best case is you find that record in the first block you read. The worst case is you find that record in the last page you read, which is N over B. Average case is what? 0.5, half of N over B blocks. Does that make sense? What about sorted files? Well, you can essentially do a binary search over the blocks you have. For that reason, it's simply log 2 of N over B. Right? You select the middle page. If the value you are searching for is less than the smallest record on that page, you can throw away all the pages coming after it, focus your search on the first half of your pages. Otherwise, you focus your search on the second half of the page, you recurse. However, this 0.5 N over B is when you assume you only have one matching record. Right? In this case, if you are selecting a non-key attribute, you do not know how many records you're going to find. What will be the cost of equality search for heap file in that case? You basically always have to scan everything before you can be sure to terminate, because you don't know whether there are more records with the matching values you are searching for. So you always have to do N over B IOs. What about sorted files? In that case, sorted file will become, you still need to pay this cost to find the first record you're searching for. And remember, there's another parameter we use, which is T, the number of records for the matching query. Suppose you have T records with that particular value. What's special about those T records in the sorted file case? Well, they must be consecutive to each other because they're sorted. So once you find the first record, you pay another T over B blocks, sequentially scan those many blocks to find all the records with matching values. That's essentially the same thing for, that basically translates to the range search cost. If you're searching a range of values, meaning if I do in this case, like that, I do have to scan through the whole page, all the pages in the heap file case to make sure I don't miss any record. Whereas in the sorted file case, I only need to pay logarithm cost to find the first record, then I just do linear scan over those T records. So far so good. Insertion cost, because we made the assumption that insertion to a heap file always happens to the last page. So insertion cost is 2. Why? Read the page, update it in the buffer, write it back. 2 IOs, read and write. For sorted file, if you assume you don't have to compact the record space, then it's simply the cost of finding the page, log 2 N over B. Remember, by that time, the page that's supposed to hold the record is already pinned in the buffer. It's already in the buffer. So you only need to update and write it back. So plus 1 is to write it back. Why log 2 N over B? Because you need to find the right page to insert this record to. That's essentially like an equality search. If you compact the sorted file, meaning you do not leave holes in pages, for heap file it's still the same thing, because I always write to the last page. But for sorted file, it becomes expensive, because you still need to do this cost to find the page to insert record. But after you, in order to do the insertion, because records are compacted, there's no space left on that page, what you have to do, you have to move all the subsequent records to slightly afterwards, and write all them back to create a space for this new record. On average, you need to read half of the pages and write half of the pages. So together, it's N over B IOs. Read and write roughly half of the pages all the time. If you do the compaction operation. Does that make sense? Similarly for deletion. Deletion is the same thing. The only thing is for heap file, deletion becomes expensive. Why? Because in order to delete the record, you need to find the page holding the record first. Meaning you need to pay the cost of searching, then plus write it back. So that's sorted file versus heap file. Now what about a B plus tree? B plus tree is nothing else but a sorted file with the fan out larger than 2. So the binary tree is I index 2 nodes per level. In a B plus tree, I index more than 2 nodes per level. So its fan out is larger than 2. And the effect of that, the header tree is smaller. So your searching cost is more efficient. With that being said, we have covered everything I'd like to cover. And I want to thank you all for paying attention during the whole course of this semester. And unfortunately, I don't have time to talk about NoSQL, but I will post some slides on it. At the end of the day, remember this word, CAP. That's the difference between relational database system and NoSQL system. CAP stands for consistency, that's C, guaranteed by your transactions. A, availability, meaning data is always available, that's guaranteed by durability. P, persistent, meaning your data is persistent through your storage. Different NoSQL systems make compromisation to one of these properties. Relational database system give you CAP. NoSQL system, in order to gain better efficiency or flexibility in terms of storing your data, they make sacrifice on one of these properties. either C or A or B. They cannot guarantee all three of them. That's essentially the motivation behind the design of many NoSQL systems. With that being said, if you understand the concept of transaction, you understand the concept of indexing and organization of data, you can easily understand the difference between relational database system, which is designed for structured data, versus NoSQL system, which is designed for unstructured data. Okay? So I will post those slides. Make sure you read those after the final test, and good luck with the final test. I really enjoy having all of you in this class. And one final thing, make sure you do the course evaluation after the final test. Okay? Thanks.
One of you rude dying. Is that?
I had a quick question. So I shown that you didn't find.
Can I ask a question? So I'm getting a 404 error, and it's kind of like random. I didn't replace my public underscore HTML folder, I don't think.
In the test string, what happens? Does the application have to have? So I'm assuming that when you ran it, this is
Just now, actually.
16 minutes ago. Do you want me to just email you, or do you want me to just comment on it like I did?
Everyone else's seemed to be working.
Yeah, so just use application.
So the files are there. I have a
Before the visit, that's where I get the clear who it is. So those are the big places I visited. I can go
I did this file, but I just put their names in there.
So anyways, that's the favorite feature. It was just giving me primary before the visit. And the other ones were race feedback and trust. So these kind of hard to get to that page and find them. So if you go to search, and if you search for house, you can change it over there to
I will discuss it with
and then it asks
Alright, I sent a message in Canvas to the teams.
with the audio. You just got one that I know is like
Can you tell us, we have a question about our phase 2 grading. Can we talk about that right now, or do you
What's your number?
40?
That is no rate feedback and no trust. I think the reason you didn't see it is because if you ask for feedback for feedback, and it's not going to ask you the rate feedback or trust because there's no feedback to see. So you just have to see one for sure. You want to check later? Okay, can I make a comment or anything, maybe?
I forgot to read my complaints.
So I just make comments on your submission.
And then the directory, so it should go home.
Okay, so I showed you.
Oh, yeah.
So
It was just one thing.
Yeah,
We had,
I'll comment how I got
I don't know if it
it.
will work on this computer or not.
We had 7. So as long as
You had
guys have
commented
feedback
that
for
we
number
didn't,
7, rate it stuff, and
we were
I'll
missing
explain that.
suggestions.
Yeah, that,
And we
have
have we have that. We just didn't have a separate class for it. We just had it named under in part of the TH class. We had a whole implementation for it here.